Hi, welcome back. What you see in front of you are two collets. These are double taper collets. Double taper because they have a taper on both sides. They belong into a valve grinding machine for automotive engine rebuilding, I think. I know next to nothing about engine rebuilding. The customer supplied me with a 10mm collet and asked me if I could make a 6mm version. Not exactly sure what's the story behind this, if these are not available anymore, but that's the information that I got. And yeah, I made a collet out of O2 tool steel, or as we call it here in the ISO world, 12842, hardened to 53 Rockwell C. The bore is lapped, and the OD and the taper are ground, are cylindrical ground. Very nice little project to make a precision component, and this is a 6mm pin. A nice fit for the collet. So let's have a look how this was made. Unfortunately, I had to rush through a lot of the filming because I'm a little bit in a time crunch, but I still want to show the process of making this because it's not a, for most shops, this is not an everyday project, and I think the way I made this can be a valuable skill. So let's have a look. I don't like doing heat treat indoors much, but it's super cold outside. Going to drop it in the oil, put sheet metal on the oil container so it doesn't catch fire or smoke the entire room. That usually works quite nicely. Okay. There we go. Very uneventful. Let's have a look. Is it cold? So I hardened this at 820 degrees Celsius. The steel I used is 12842, which is similar to O2 in the US. This is as hard as it will get, and now we will draw it back to 52 Rockwell C, which is a good hardness for a collet. The hole in the center is pre-drilled 5.8mm, and I will finish it after I'm done with heat treating. I will try to run a carbide reamer through it instead of trying to ID grind such a long, thin bore. ID grinding this, this is 6mm diameter and 55mm long. That's almost 10 times diameter. That's, with my equipment, really annoying to ID grind. For hardening, I had painted the blank in this stuff. Luiso W61. You have to Google this yourself. I have no idea where to get this. This is a scaling paste that you paint on to prevent scaling. It's a super thick black goo that's water soluble. And you paint it on, you dry it. I usually speed up the drying on a hot plate. And this protects the item that you're heat treating from the oxygen environment in the oven if you're not using a vacuum furnace or an inert gas environment furnace. This is very similar to using a stainless steel bag, probably a little bit less good of a protection, especially if you purge the stainless steel bag that you wrap your part in with argon. But for something like this, it's totally fine. So cleaning up the collet blank on the sanding plate. The hardness tester needs a clean surface. The surface where the diamond indents on needs to be relatively good, and the surface that rests on the anvil of the hardness tester needs to be rather good too, so the part doesn't settle or move while being indented. This is just a €55 granite surface plate that I got from the woodworking supply. Woodworkers seem to use them to check the sole of their hand planes for flatness using these. And I inspected it, and it's a surface plate. It's really, really flat. And I just purchased some 400 grit silicon carbide paper and stuck it on here with spray adhesive. Robin Ruan said you did a video on the whole process called the magic sanding plate, and yeah, it's magic. It's really nice if you have a very, very flat piece of sandpaper in your shop just to clean up things. Not for precision work, but just for cleaning. Over here in the corner we have Professor Dr. Wolpert, which is my hardness tester. It's always here for me to check stuff for hardness. So let's see. Okay, we got our preload. Now I will have it indent. Okay, it's settled out. We wait a few seconds. And when I drop the lever, we will get our real hardness reading. Yeah, that's 63 Rockwell C. That's about as hard as O2 will get. Had it in the oven for 1 hour at 350 degrees Celsius. This should give us 54 Rockwell C. Okay, let's check hardness after tempering. Yeah, that's 53 and a little bit. Now after hardening, this collet blank is probably warped in every possible direction. So I need to get a reference. And in the past I learned that when making a collet like this, the bore is the best reference because I can put a arbor in it, an arbor that I grind between centers, press it in, and use that as a reference from there on. So now we need to finish the bore to a precise diameter, a nice bore. And usually I either hard bore them and then lap them, or in this case I will try something new. This is a carbide tipped reamer. A standard machine reamer, 4 flute, 6mm, and we will just run this and hopefully don't chip it. There we go. That was reaming. The reamer is held in a floating reamer holder. This is a small Rigofix floating reamer holder with ER 20 collets. And this allows the reamer to move along with the bore. Since the part has some heat treatment warping, you can't indicate it anymore to be coaxial or parallel with the spindle of the lathe. So the floating reamer holder in this place is very important. So I had to pause because I was giggling like a little schoolgirl. But this the carbide reamer in the hardened O2 worked way too good. This worked way better than it has any right to do. This is a 5.99mm gauge pin, and as you can see, this is a nice sliding fit. I will cobble together a lap, and I will open up the bore to be a sliding fit on a 6mm pin. So straighten out the bore finally and make it round and on size everywhere. Now it tapers a little bit to the back according to the pins. Splitting the end of this is 6mm brass, and I drilled and tapped the end with an M3 thread. Now I'm splitting it with a small handsaw. Twice, 90 degrees offset to each other, just eyeballing. Back in the lathe, and I have an M3 screw with a little bit of molybdenum disulfide grease on it to help us, because screws in the labs tend to bind and seize. The screw is now bottoming out in the thread, and the tap I use has a lead out, of course. And when I continue to tighten the screw, it will expand the end of this lap. And this is our size adjustment. It's as simple as that. I will give it a little bit of preload, and then I will turn the OD of the lap to 5.98 millimeters. I machined the lap to 5.98 in front here. Let's double check. Yeah. 5.983, and about to half the length of the bore. And I relieved this end here so I can pass through the collet without getting into trouble. Sorry if I'm speeding through all of this a little bit, because this part kind of needs to get out the door, but I still want to film it, because making a collet is something that's a little bit obscure and not everybody has a good idea how to do it. And this is already the second one I make this way, and I know this approach kind of works. So using 400 grit silicon carbide lapping compound. I like this stuff because it's the most mess you can imagine. Just applying a little bit here. A wise person would use gloves. Also, I have a towel on the way cover. I don't need abrasive lapping compound on my way covers. That's not as bad as on the lathe ways, but still, I don't need that. Our favorite oil. This is not WD-40, this is just petroleum. And our collet blank. I will start a kind of slow RPM, 330 RPM, and I will just see how it behaves on the lap. This will both size and condition the lap and the part. I can already feel that, I flipped it around, that this is the tighter end of the bore. Out here it's an easy sliding fit, and the further down I go, the tighter it gets on the lap. So I will, since only this end of the lap is actually nominal diameter, I will concentrate working on this end of the bore. Ooh. Uh-oh. That's a problem. Let's see if we can remove a little. Oopsala. Let's add a little bit of tension. This is all experience and feel. Okay, and we already can see that there is a mix of brass and black slurry building up on the exit of the board. That's part the lap that's being abraded, and part the silicon carbide that's breaking down into finer and finer particles, and part the steel that's being cut. So let's clean the bore and check with gauge pens. I cleaned the bore of the part, and I have a 5.98 millimeter gauge pin here. So 20 micron under nominal. These old boxes are disgusting. The foam in the cover disintegrates and creates so much dust. The old Mitutoyo boxes are the same. So 20 micron undersize. Very loose. Well, it's a sliding fit. That's 10 micron under nominal. That's a very nice tight sliding fit. So, and a 6.0 nominal, 6.00 nominal pin. Idiot checking so nobody put the pin in the wrong spot of the box. 5.998. So that's nominal pin. It wants to start on this side, and it kind of wants to start on this side too, but not really. It wants to start on this side. So this side is still a little bit smaller in diameter. So back to the lap it is. At some point you notice that the part moves very free on the lap, then it's time to adjust the preload a little bit. And you're kind of using the lap like a gauge, depending on the force you need to hold the part, to prevent the part from spinning with the lap. That tells you very precisely where you need to move your part and where to remove material. So let's check again. Okay, I don't want to rearrange the camera. 6mm pin goes in from side 1 almost all the way to center line, and from the second side it's the same. So this tells me that the bore is barrel shaped. It's tighter in the center and the ends are a little bit bell mouthed. So I will concentrate the lap in the center of the bore. And you might notice that each time I'm going to the lap and I take a little bit of material off, I'm not I'm maybe taking 2 or 3 minutes each time, then go back and check. This is relatively quick. And 6mm pin part. That's a sliding fit. I will go with a little bit more with the hone. This is a little bit too tight for my taste on a nominal sized pin. I'm going to leave it like this. This is the 6mm pin. It's a nice sliding fit, but not loose. So I'm going to leave it like that. The pin, well, the hone will go in my box with hones if I ever need to do another 6mm bore. This is looking good. This is progressing very quickly and very easy. Over at the surface grinder, and I have an old friend set up. This is the center set for cylindrical grinding that I made years and years ago that I need to rebuild very much because this has a bunch of design flaws. For example, driving your workpiece with... So there is a spring-loaded center, so you can take your part in and out of the fixture, but in a... I'm not sure why I did this. The drive dog runs on the spring-loaded center, and this is truly not ideal. This puts a little bit of wiggle on the center here, because since it's spring-loaded, it's not clamped, it can move around, and that's a little bit of a problem. Also, the drive disc is not really needed. The better way to drive parts on such a fixture is just running an O-ring, like a belt, directly on the part. So that's the two things that I will change on the next iteration if I ever build another one. Holding it in a grinding vise, and I have a dial test indicator here, so I took a brass piece or copper piece and I knocked the fixture around until it ground parallel. Well, not parallel, 8 micron taper. Smaller here, bigger here. So I ground this arbor here. Just between centers. This is soft steel. This has only to hold up for one part. It's 6.008 here and 6.000 here. I'm going to demonstrate. 6.008 here on the thick end and 6.00 out here on the open end. That's a very common way for work holding on cylindrical grinders. You have a minor tapered arbor that you press into your workpiece. And since this arbor is ground in the centers, it's running reasonably good true. Now I can just press my collet blank onto this arbor, and then I have 2 centers that I can use to OD grind the features on this blank to the ID, and everything will be running true and all will be hunky-dory. So I'm going to press this in, adding a little bit of oil around my press fit here. A very mild press fit, so it shouldn't require a ton of force. Yeah. There we go. Finished the 2 outer diameters. These are not really critical dimensions, so I didn't bother with super tight tolerance here. It's a tad undersize. I measure 3 micron undersize. That's okay. This is not a functional surface here. But it's still nice to hit, to make it kind of nominal. I kicked the grinding fixture at 15 degrees with an angle block, and I indicated it in, just tapped it in with a hammer until I get a 0, 0 reading end to end on this angle block. I checked these angle blocks piece by piece against a sine bar, and they all are darn good for general shop work. And the taper we're grinding is relatively short, so indicating on such a long distance compared to the short taper we're grinding will make things better. You might ask why I didn't rough out the taper on the lathe and I'm grinding all of this. And the true answer is I couldn't be bothered to rough it out on the lathe. Grinding this will go quite quickly. We might have to press the arbor out and put it in the other way to grind the second taper. So this goes between centers like this. That's fine in my book. Keep in mind this collet goes on a valve grinder for automotive purposes. I'm not sure how much of a precision machine a valve grinder usually is, considering the environment they get run. There are probably rather nice machines, but also probably a chunk in precision between a valve grinder and a real tool room machine. But I could be completely wrong here. So we definitely will try to do an as good as possible job with this collet. You see how quickly that goes. I'm taking 50 micron downfeed passes, and then I'm feeding the edge of the wheel across the part. The edge of the wheel is doing all the work. This is a Norton 3SG seeded gel or ceramic grinding wheel, and the edge on these holds up really, really well. This is really my preferred wheel on such a light duty machine for round work. I ground the first side, just calipered the small diameter here to my final diameter. This is not a critical size, the angle is important. And now I need to flip it around and grind the taper on the second side, but I think I'm going to press the arbor out and put it in reverse. Ground the second side. So now we can figure out how to cut the 3 slits on each side into it to make an actual spring collet. Let's get the arbor out. So I slit the first side of the collet using an abrasive wheel and a surface grinder, and the part was pushed onto a 6mm ejector pin, and I had some super glue on here, and the end had a toolmaker's clamp, so it can't get yeeted off by the wheel if the super glue fails. That worked okay, But for the second side, I figured I'd take the same ejector pin and I slide the part up all the way to the head of the ejector pin. So it's already captive. Then I take a hose clamp and I clamp the already slit portion of the collet to the ejector pin shaft. Am I the only person in this world who does not like magnetic screwdrivers? It's the most infuriating thing ever. Or magnetic bit holders, for that matter. There we go. This hose clamp collapses the collet onto the shaft, clamps it in place. Now I can put it in my spin fixture and do the slits on the second side. I have to take the hose clamp off again to align the slot in the collet with the wheel, so I can index it by 60 degrees. So I get an even pattern from side to side of the collet. And for this, I'm just going to move the table in. I'm just going to drop the wheel into the slit of the collet. I can get the hose clamp back in place. The hose clamp is basically just for added security. There we go. Now I can index by 60 degrees and cut my slots 120 degrees apart from each other. So here is the finished collet. After slitting, I deburred it with die grinder carbide burr on the outside and some Scotch-Brite. And I use a triangular stone to deburr the inside of the slots. I was a little bit worried that it might move in a funny way when I cut the slits, but with a 6mm carbide pin, this is still a very nice sliding fit in here on the pin. Really a nice result, ready to ship out. Spray it down with some rust preventive and box it up. I had unfortunately to rush through a lot of this. That's why the video quality on this one is atrocious in parts, but I think it's still important to show a way how to make a collet like this and show an approachable way to do so. On a larger collet, I would not use a carbide reamer to hard ream the blank. I would either hard bore it with a solid carbide boring bar, or ID grind it with an air turbine spindle on the lathe. And then lap it to final fit and geometry. Hope you enjoyed, thank you all for watching, and thanks for the support. I'll be back.